Hi everyone. Today we are going to see how to measure the potential difference across the resistor by using potentiometer. Let us say we want to measure the potential difference across the resistor like this. Yeah, let us assume that R1 is its resistance. So let us assume that I1 is the current flowing through the resistance R1. Okay, right. The potentiometer circuit, which is used to measure potential difference across the resistance, can be represented in a simplified form of circuit like this. You can see now. It consists of long wire AB of uniform cross section in series with here battery E0 and rheostat R0, which is kept at a suitable position so that a constant current I0 flows through the main circuit. This is called main circuit of the potentiometer. A, B, C, D, A. Yeah. In the sub-circuit, resistance and galvanometer are connected in such a way that junction A is connected to here. So when current flows from left to right, so we know that current always flows from higher potential to lower potential. We indicate positive sign here, negative sign here. That is the thing. Yeah, this is a I1 current entering like this. This is going to leave. Yeah, that means this resistance R1 is part of another circuit. Okay, but across the resistance R1, what we are connecting? We are connecting potentiometer. You can see here junction A is connected to positive terminal of the resistance R1. You can see negative terminal is connected to galvanometer. The moving contact J of the galvanometer is kept in contact with wire AB. You can see that is the thing. So these terminals, let us name AE, FJ, like this. Yeah. First of all, we are going to obtain the expression for current flowing through the galvanometer. Okay, right. Let us say the moving contact J is at arbitrary position. Arbitrary position means what? It can take any value. When it is at arbitrary position, let us say I is the current flowing through the galvanometer. Small I is the current flowing through the galvanometer. Current that is leaving the junction A, like this. Yeah. Now let us focus on the junction E. So at the junction E, you can see I is the current entering, I1 is the current entering. Yeah. Let us say IR1 is the current flowing through the resistance R1. Okay. Yeah. So what is that IR1? So for that we need to apply KCL at E. What the KCL states? At any junction, algebraic sum of the currents must be 0. So that is the thing. Let us take a entering current as positive. So then leaving current is going to be negative. Leaving is going to be negative. So when we apply KCL at E, what we are going to get? So I and I1 are entering currents, you can see. So they are going to be positive. IR1 is leaving, so it is going to be negative. So yeah, so we are going to get from KCL IR1 is equal to I plus I1. Right. Let us focus on the junction A. At junction A, you can see I0 is the entering current, I is the leaving current. What is the current flowing from A to J? Let us take it as IAJ. So let us obtain IAJ in terms of I0 and I. For that, what we need to do? We need to apply KCL at A. So when we apply KCL at A, junction A, Yeah, I0 is entering current, that is going to be positive. Yeah, I and IAJ are negative. So here why they are negative? I and IAJ are leaving currents. So leaving currents are negative. So I and IAJ, algebraic sum must be 0 from KCL. IAJ we are going to get I0 minus I. Right. In order to get the current expression, we need to apply KVL to the sub-circuit. Okay. To make things clear, let me draw the sub-circuit again. Yeah. So we know that in the sub-circuit we have resistance R1 and galvanometer. Let us say galvanometer resistance is Rg. So now this is R1. Between A and J, what is there? Wire is there. So between A and J, wire is there. Let us say RAJ is the resistance of the wire between A and J. Right. Here you can see what is the current flowing through the R1, that is nothing but IR. IR1 is I plus I1. Yeah, so this is I plus I1. So here you can say I1 is flowing away. I plus I1 is coming, I1 is flowing away. Which current will come? I current will come through the galvanometer. So current flowing through the galvanometer resistance is small I. Yeah, what is the current flowing from A to J? So that is IAJ, I0 minus A. So that also we can write. We know that current always flows from higher potential to lower potential. Yeah. So we indicate positive sign like the negative sign, positive sign, negative sign like this. Here also current flows from higher potential to lower potential. Like this we indicate. So when we apply KVL to this loop, AEFJA. So what we are going to get when we apply KVL to this loop, AEFJA. Yeah. So we are going to get minus I plus I1 R1 minus I into RG plus I0 minus I RAJ is equal to 0. So when we separate the terms, what we are going to get? I0 RAJ minus I1 R1. So here items R3 we can see. So when we take other side, we are going to get R plus RG plus RAJ. So we are going to get I as I0 RAJ minus I1 R1 by, sorry, this is R1 plus RG plus RAJ. So we got current expression. Let us move to next whiteboard. Yeah. So just now we got current expression I0 RAJ minus I1 R1 by R1 plus RG plus RAJ. So this you can see just now we obtained. Yeah. So let us take it as equation 1. What this I0 RAJ terms represents, for that we need to refer to Ohm's law. So we know that Ohm's law relates current flowing through the resistor, okay, and potential difference across the resistor, or we can say current flowing through the resistance and potential difference across the resistance as like this, V by I is equal to V by R. Let us say here you can see where I is nothing but current flowing through the resistance R. V is nothing but potential difference across the resistance R. Right, that means V is equal to IR. What this I represents in IR product? That represents current flowing through the resistance R. Right. So when we apply this to I0 RAJ, what we are going to get? What this I0 represents then? So that I0 represents current flowing through the resistance RAJ from Ohm's law. Clear? So what this product I0 RAJ represents, you can see from Ohm's law. That represents potential difference across the resistance. Here what resistance? RAJ in this case. So this represents potential difference across RAJ. Here RAJ is present between junction A and moving contact position J. Potential difference across the RAJ means that is going to be VAJ. Potential difference across RAJ, that is going to be between A and J. So that is VAJ. Clear? So we can also apply this Ohm's law to I1R1. That is also what I1R1 represents. It represents potential difference across the R1. Okay, potential difference across R1. So you can see. So as R1 is present between E and F, potential difference across R1 means that is going to be BF. So that is it. So here I1R1 is nothing but potential difference across R1, that is VF. So let us take this as equation 2, this is equation 3. So when we substitute this into equation 1, we are going to get I is equal to VAJ minus VF by R1 plus RG plus RAJ. Yeah. Here, what is our objective? Our objective is to find potential difference across the resistor. Okay. So that is nothing but VF. So the potential difference across the resistor means that is going to have some fixed value. It may be 3 volts or 4.2 volts or some value, some fixed value. So that is the thing. Right. Before going to experimental procedure, let me make certain things clear. Okay. For that, let me draw the circuit diagram again here. Yeah. So potentiometer circuit consists of main circuit in which wire AB, battery E0, rheostat R0 are connected in series. That we know. Right. In the sub-circuit, we have resistance R1 and galvanometer like this. Yeah. Right. When we move the moving contact J on the wire AB, what happens? So let us say when we move the moving contact J on the wire AB, what happens? Here you can see the junction A position is fixed. When we move the moving contact J, what happens? Length of the wire between A and J varies. So that is the thing. When that length varies, length of the wire between, let us say LAJ. So when that varies, resistance resistance of the wire, that is proportional to length of the wire. So that also going to vary. When RAJ varies, you can see the VAJ, which is proportional to RAJ from equation 2. So that is also going to vary. So like this, when we move the moving contact J on the wire AB, what happens? As the length of the wire varies, resistance to RAJ and VAJ, potential difference, they are going to vary. Yeah. So that means the equation 4 we can write when we move the moving contact. So they are going to be like this: R1, RAJ. So RAJ varies, VAJ varies. When these vary, current also varies. So that is the thing. Right. Here VAJ varying. So in the range of variation of VAJ, our objective VF is going to present. So that is the thing, right? Of course, they design like that. Let me make it clear through example. Yeah. So let us say when you move the moving contact, VAJ is varying from 0 to 5 volts. So let us say VF value is 4.2 volts. You can see 4.2 volts is present between 0 to 5 volts. Yeah, that means for a particular position of moving contact, the VAJ becomes equal to VF. So for a particular position, VAJ becomes equal to VF. When these two become equal, what happens? From equation 4, you can see current becomes 0. That is it. So when what is that? VAJ becomes equal to VF, current becomes 0. Or in other words, when current becomes 0 in the sub-circuit, what is happening? Current becomes 0 in the sub-circuit. What is happening? VF is becoming equal to VAJ. Our objective VF is becoming equal to VAJ. Okay, so that is the one. At 0 current condition, we are obtaining our objective. That we have to understand now. So that's why to detect the zero current condition, galvanometer is kept in the potentiometer. That is it. Okay. Now we are in a position to understand the experimental procedure. The experimental procedure is to move the moving contact J on the wire AB and obtain zero deflection of galvanometer for a particular position of moving contact. Okay. So that at that particular position or zero deflection condition, our objective here VF becomes equal to potential difference between junction and moving contact position. So that is it. Clear? Right. So let us say when the moving contact J is at position 3. So when the moving contact position 3, galvanometer shows zero deflection. That means current becomes 0. Let us say. Right. Yeah. Here what is happening? When the moving contact at position 3, galvanometer is showing zero deflection. That means current is becoming 0. When we substitute this into equation 4, what we are going to get? 0 is equal to J position 3. When we substitute in place of J3, we are going to get RG plus RA3. So as LH is 0, we are going to get our objective VF is equal to VA3 is equal to how much from equation 2? I0 RA3. So VF is nothing but I0 RA3. By knowing I0 and RA3, we can obtain our objective here. But the standard practice is, standard practice is to replace the standard cell, okay, in place of resistance R1, okay, and obtain the zero deflection of galvanometer. So that at that condition, okay, so at that condition, we can obtain EMF of the standard cell, okay, in terms of circuit parameters, just like I0 and resistance of the wire, okay. So you can see now. So in the what is the standard practice? Resistance is replaced with standard cell like this. Now you can see. Yeah. So this is part of the circuit is going to be remain same, main circuit. So that same current will flow through here I0. Yeah. Right. So in place of resistance R1 or in place of resistor R1, we use standard cell like this. And same galvanometer is used. Yeah. Right. So here we are going to repeat the experiment for this case. So here what is the current expression we are going to get for this case? So that is going to be VAJ minus ES in place of potential difference across the resistor and resistance R1. We are going to get cell parameters ES and RS. That is the only difference. Of course, this I derived in the class. That is a measurement of EMF of the cell by using potentiometer. If you want, you can go through that. So I provide link in the description. So that is the thing. So this is RAJ. So let us take equation. This is equation 5. So this is equation 6. Yeah, same. Repeating the experiment means what? We move the moving contact J on the wire AB. Yeah, and obtain the zero deflection of galvanometer for a particular position of moving contact. So that at that particular position or zero deflection condition, our objective in this case, EMF of the standard cell, becomes equal to potential difference between junction and moving contact position. Here, the interesting thing is ES is known, so that we have to note. Okay, standard cell EMF is given. Yeah, here. So let us say when the moving contact J is at position 2, so galvanometer shows zero deflection. So when we substitute into the expression, what we are going to get? Yeah, 0 is equal to VA2 minus ES RS plus RG plus RA2. As LHS is 0, what we are going to get? ES is equal to VA2, that is equal to I naught RA2 from equation 2. So this is going to be 7. Yeah. So here we can see ES is nothing but I naught and RA2. One more thing in this, to measure the length of the wire between junction A and moving contact position, for which galvanometer shows zero deflection. Yeah, a scale is kept below wire AB like this. So this is a scale which is kept below wire AB. So divisions are going to present to measure the length. So it is, yeah, same here also. So divisions are going to be marked to measure the length. Right. It is used to measure the length of the wire between junction A and moving contact position, for which galvanometer shows zero deflection. In the first case, LA3. In the second case, that is going to be LA2. So which are to be used in the next part. Let us move to next whiteboard. You can see equation 5 and 7. We obtained EMFs in terms of main circuit parameters. Yeah. Right. So what we got? VF is I naught into RA3. What is second case? I naught into RA2. What is RA3? RA3 is nothing but resistance of the wire between junction and moving contact position 3. So we know resistance of the wire is rho, in this case LA3 by A dash, where rho is resistivity of the wire. Okay. A dash is area of cross section of the wire AB. Okay. So LA3 is nothing but length of the wire. Similarly, RA2 is equal to rho LA2 by A dash. So in the two cases, we use the same wire AB of uniform cross section. Therefore, rho and A dash are common in the two cases. Okay, when we substitute into this equation, what we are going to get? Yeah, VF is equal to I naught RA3, rho LA3 by A dash. Yeah, here you can see these are all constants, I naught, rho, A dash. Okay, so let us take this I naught, rho, A dash as A, some constant A. So yeah, A into LA3, that is the thing. Similarly, for ES, what we are going to get? I naught RA2 is rho LA2 by A dash. Here also these are constants. So value of this is also going to be same. A. So ES is equal to A LA2. You can see here. Let me take it as equation 8, and this is 9. Here VF is proportional to LA3. It is only depending upon length of the wire, length of the wire for which galvanometer shows zero deflection. Here also ES is equal to, it is only depending on length of the wire for which galvanometer shows zero deflection. That is, so when we take ratio 8/9 equations, what we are going to do, VF by ES is equal to LA3 by LA2. Yeah. So VF is equal to what we are going to ES into LA3 by LA2. So this is known, and these are measured from scale. So by substituting, we can obtain potential difference across the resistor R1. Here you can see we are only measuring LA2 and LA3 from the potential experiments and obtaining potential difference across the resistor R1. So that is the thing. Yeah. Today we have learned about how to measure potential difference across the resistor by using potentiometer. The working principle is when the galvanometer shows zero deflection, the potential difference or EMF becomes equal to potential difference between junction A and moving contact position J. So that is it. Thank you.